Hello, hello. We're going to move on in our unit of polynomials, and we're going to pretty much pick up where we left off with naming polynomials and talking about degree and number of terms and all that stuff with combining like terms, because we touched on something in that last lesson that fits totally in, and it's understanding what a term is. And remember what terms are. They're pieces of math separated by plus or minus sign, and they have a unit of measurement. So here's that note that we had taken last time, right? So what is a term? A piece of math separated by a plus or minus sign. It has a unit of measurement. Okay, what are units of measurement? We talked about something we can measure like distance, time, or weight, or anything like that. We talked about categories, but mostly we talked about dimensions because that's where this picks off. If you remember, we have one dimension, which is length, u to the first power, or any variable to the first power. We have two dimensions, which is area, any variable to the second power, and then a dimension in the third dimension, which is volume, or a unit to the third power, and that's cubic units. And as we remember, that length and area and volume are completely separate ballparks, and so a variable to the first power is completely a separate ballpark to, even though that same variable but to a different power. They're completely separate and they're not like. And so we know that like terms have the same unit of measurement. Okay, so we're going to bust off of that note and get into a fairly quick lesson on combining polynomial-like terms. So for each one of these expressions, we've got some craziness going on there. And what we're going to do is identify which terms are like and then combine them. Okay, so we're thinking of units of measurement. So I'm going to rewrite each one, but I'm going to rewrite it, reading it a little bit differently. Okay, so this first term is -6. That's how many x squared y's there are. Okay, so there's -6 x squared y's. We're going to add 2 xy squareds. We're going to subtract an x squared y, and then we're going to subtract 5 xy squareds. So when we read that thinking in units of measurement, hopefully you heard yourself identify basically two different units of measure. We have x squared y's and x squared y's, and we have xy squareds. Okay, so when you're reading things out loud, we're going to be better able to identify which terms are like by looking at it in terms of units of measure. Once we have identified the common units of measure, we can then rewrite the statement. And you don't have to do this, but I'm just demonstrating it. You can rewrite the statement using the commutative property of addition. Okay, so I'm just going to take my x squared y's, and I'm going to put them close to one another. Now keep in mind how this works is that we have signs that belong to each term. So this is x squared y here, but this negative here belongs to it. Okay, so this negative sign we're going to rewrite with it, and we're going to just put it next to that -6 x squared y. And then come our 2 xy squareds. So this is 2 xy squareds, but there's a plus there, right? So plus 2 xy squareds. And then this looks like 5 xy squared, but it's that minus sign belongs to the 5. So we're going to rewrite that using that. Now you don't have to show this work if you understand what's happening, but it's healthy to know. So now we have, again, all of these confusing variables and exponents and stuff. But if you're thinking in terms of units of measure, everything becomes a bit simpler. Remember, this unit of measure is x squared y. So there's -6 of them. So we have -6 x squared y's, and then we're taking away how many x squared y's? How many x squared y's is this? It's only one of them. So we had -6. We're taking one of them away, so we're looking at -6 minus 1. Okay, so we're thinking -6 minus 1 is -7. So how many x squared y's are there? -7. And now we have plus 2 xy squareds, and we're taking away 5 xy squareds. So what's 2 minus 5? Of course, -3. So we have negative 7x squared y's minus 3xy squared. These, of course, are two different units of measure, so we cannot combine them. We are as simple can get. So this is the simplified expression. And for the previous unit, we would say that is the previous lesson, we would say that is a second degree binomial. In case we're looking at this craziness, it's actually a second degree binomial. So when you read things out loud, a lot of things become simpler. And so I'm going to do the same thing with this expression in number 2. I'm going to read it out loud, thinking units of measure, and then I'll be able to perform the operation, hopefully a little bit quicker, so we can see some things that are happening. So we have negative a to the third powers, whatever that means, plus 2a squared b's minus 4ab squareds. So far I haven't heard any same units of measure, plus 5b to the thirds minus a squared b. Hey, that rings a bell. Feels like we mentioned that before. Plus ab squared plus an ab squared. So minus an a squared b plus an ab squared plus an a to the third power. All right, so when I rewrite it, you thinking of units of measure, some things start clicking. All right, so I have minus an a to the third power. And then I feel like I said a to the third power somewhere else, and it was over here. So that's minus an a to the third power plus an a to the third power. You know what happens? That completely cancels. No more a to the third powers. They're gone. So that completely cancels out. And you can look at it in terms of this way. Minus plus is gone, right? It's totally gone. And so now we had plus 2a squared b's. Are there any other a squared b's? And yes, remember we took away an a squared b. So we had 2a squared b's minus an a squared b. How many a squared b's does that leave us? 2a squared b's minus an a squared b leaves us with 1a squared b. So we would write just 1a squared b, right? And you may think, well, you said 1a squared b. Where's your 1? I don't need a 1. There it is. That's 1a squared b, right? That's an a squared b. So there's only one of them. Thinking in units of measure. And now we had minus 4ab squareds. So here's minus 4ab squareds, and here's plus an ab squared. So minus 4ab squareds plus an ab squared would leave us with minus 3ab squareds. So minus 3ab squareds. And then we had our plus 5b to the third powers. Are there any other 5b to the third powers? No. So I'm left with 5b to the third powers. And that is my simplified expression because these are all different units of measure. Okay, since they're all different units of measure, they're not like terms. That is as simple as we can get it. Okay, so see how it's becoming a little bit quicker when you're thinking in terms of units of measure. Now, for number 3, do the same thing. I'm going to rewrite it thinking units of measure. I have 49x squareds. I have plus 42xy's. And then I have minus 42xy's. And then minus 36y squareds. Okay, so hopefully you see what's going to happen. Okay, so I have a unit of measure, my x squareds. There's no other x squareds. That stays the same. I have plus 42xy's, minus 42xy's. What does that leave me? No more xy's. So if my xy's are gone, I can just mark them off like that. My xy's are gone. And that leaves me with minus 36y squareds. So I have minus 36y squareds. And that's as simple as I can get it. Now, why did I put this one? It seems easier than number 2 because I'm giving you a lead-in. Hopefully you notice something interesting about this particular expression. Notice how we are subtracting two different things, right? So this is called a difference. A difference of something special. Do you know that 49x squared is what's called a perfect square? So 49x squared is a perfect square. It's 7x times itself. And then 6y squared is 6y times itself. So this is called a difference of squares, right? because 49 happens to be 7x squared, and 36y squared happens to be 6y squared, and we're just subtracting them. So that's just an interesting thing to look at. I figured I'd show that because we're going to see that again in the future. But as far as combining like terms goes, we're done here. That's called a difference of squares. Just so happens it works out that way. And that is basically it. So we're just piggybacking off of the previous lesson on combining like terms and seeing how that works. If you look at it in terms of units of measure, everything works itself out. Thank you.